All right, well, let's move on. The first session, first half of this talk will be about exploring data. Darren and I, when we were planning this, we thought, what can we do that might actually be helpful for teachers right now, right? You might be in your linear regression unit, certainly be coming up on probability and random variables soon. So we're hoping to provide you with some useful stuff that you can use with your students this year. So I'm going to be talking a little bit about R squared and S, the standard deviation of the residuals. And we're going to use a context that might be familiar to some of you. It's based on question 1 from the 2022 AP Statistics exam. We're not going to do the whole question, but it is a nice small data set that we can enter on our calculators and play along and ask some really interesting questions, including a couple questions that were asked on the AP exam where students did maybe not so well. So hopefully we can point out some of those common errors and help your students avoid them. All right, so a biologist gathered data on the length in millimeters and the mass in grams for 11 bullfrogs. Here are the data. Okay, so part A says, make a scatter plot to display the relationship between y equals mass and x equals length for these 11 bullfrogs. Describe what you see. So I'm going to pause for a minute. If you want to play along on your calculator, which would be encouraged, I'll give you a minute or so to enter these data. Go ahead and put length into list 1 and mass into list 2. So you can see, I'll pull my calculator up here in a second. But you want to put length into list 1 and mass into list 2. So just a comment while you're doing that. On the 2022 AP exam, part A actually gave the students the scatter plot and then asked them to describe it. Here, because we're trying to be a little bit more active and highlight some calculator features, we're actually going to make the scatter plot and then go ahead and describe what we see. But on the actual AP exam, the scatter plot was provided. Okay. That being said, just again, a side note while you're entering the data, it has seemed to be a pattern over the last several years that students have had to make some sort of graphical display. Last year, it was a box plot. I think the previous year, it was maybe a bar graph or a segmented bar graph. All the years are kind of blending together, but I know that the last several years, students have been asked to make some sort of visual display on the AP exam. So don't be surprised if that happens this year. So anyway, let me get out of the PowerPoint for a second and pull up my calculator. So I've also entered the data ahead of time. I don't always remember this for class, but here I remembered to enter my data ahead of time. So that's right there. And then to make the scatter plot, okay, so I saw that a little bit there. So to enter the data, sorry if we're unfamiliar with that, we're going to go to Stat and then press Edit. Okay, and have the data entered into list 1 and list 2. Once they're there, we want to make a scatter plot, right, to see this association. Okay, so we're going to go to second and then y equals, which is stat plot. Okay, so it's not the y equals menu where you enter functions. It's second y equals, which is stat plot. That's where you can choose to make scatter plots and box plots and histograms and other sorts of graphs. So we only want to use one at a time. So we're going to go to plot 1, which is where our cursor defaults. Press enter. Depending on what you've been doing recently on your calculator, this might be on or off. So you want to make sure and go to the on button, hit enter. Okay. And go to type. The first type is a scatter plot, and that's what we want. So make sure your cursor is blinking on that and then hit enter to make sure it's selected. Okay. The other graphs, if you're not that familiar with the TI graphing calculator, the second one is what you'd use to make maybe a time plot. It's kind of a connected scatter plot where it connects the dots in the order that you enter them in the lists. Then you have a histogram. You have a box plot that marks outliers separately if there are any. Then you have a simpler version of a box plot that you might use, in earlier grades that doesn't necessarily doesn't mark outliers separately. And then at the end, you've got this thing that looks like a scatter plot that's actually a normal probability plot. something that's an optional topic for AP Stats. Okay, so we got all that. Here's list 1 and list 2. So if your calculator maybe is defaulting to that, but if you don't have those there, you have some other list. The list button, you can press second and then the number 1, and that gives you list 1. You can see the blue L1 there. And then go down to Y list, and you want to do second and the number 2 to see list 2. Okay. Mark, you can choose whatever mark you want, but I like the big squares because, you know, old guy with hard to see the dots there. So do that, and then choose your color. Right. So blue's what I have, so I'm going to go with that. We're going to press zoom, which is in the top middle up here. Zoom. You could press graph, but it's unlikely that you'd see the scatter plot because it's going to graph whatever window you had previously. So for statistics, a really nice feature is number 9, zoom stat. Okay, what that's going to do is it's going to put your data in a nice window with just a tiny little buffer, and it's going to have your data fill the screen as much as possible, so you don't have to strain your eyes. All right. So there's our scatter plot. Okay, there's our scatter plot. So let's go back to the PowerPoint. So I had these screenshots there just as in case my calculator, you know, fritzed out or something like that, or I got confused. So here's what we see. Now, this was part A on the actual AP exam. And so they were looking for several things when they were asking for the description. In fact, whenever you're describing a scatter plot, there's 4 things you have to describe as far as characteristics, and you have to describe it in context, right? So you have to describe direction, in this case positive. You have to describe form, which in this case looks linear. Our options are basically linear or nonlinear. I just taught this lesson this week with my own students. And I tell them that if it's kind of a big blob and you can't really, doesn't seem linear, as long as it's not curved, our sort of default is linear. And then strength is how close those dots are packed around whatever form you've decided. So if you've decided it's linear, then how close are those dots packed to where a line would go through? And so this looks moderately strong, not a whole lot of scatter. And then the 4th thing, so we've got direction, form, strength. The 4th thing is unusual features. Unusual features. So that would be clusters or outliers. There's possibly an outlier there. I don't know if you can see my mouse, but sort of in the lower right, there's possibly a bullfrog that seems a little bit light for its length. Maybe it's on a diet or something like that, or maybe not a lot of flies in that area for tasty snacks. I want to emphasize one point, and that is in the past, for my students, I've said, oh, if there's no unusual points, you don't need to say that. Just move on, okay? But I've now changed my advice to my students. Based on recent rubrics, they've had 5 components: direction, form, strength, unusual features, and context. And the unusual features, you get credit for that, even if there are none, as long as you say, and there are none, no unusual features. So that's kind of a free component, you know, but don't miss it, right? Just because there might be nothing unusual, go ahead and have your students comment, and nothing unusual, no outliers, no high leverage points, no clusters, things like that. That way you can have some margin for error on those questions. And of course, context. For context, you have to mention the variable names. So we don't see the axis labels here, but essentially that's what you need to be thinking about, is saying the axis labels. So talking about bullfrogs and the biologist, not going to give you credit for context. What's giving you credit for context is the variable names, length and mass. And then you should talk about bullfrogs, so it's clear that you're not talking about, you know, horses or elephants or other things like that. So here is a model solution. It says there's a moderately strong, positive, linear association between mass and length for these 11 bullfrogs, with a possible outlier at 162, 350. Okay. When you're describing that possible outlier, I mean, we have the data set here, so I know what point it is exactly. If the students were just provided with a scatter plot, they could, you know, estimate what the coordinates are, and there's a, you know, pretty generous in terms of our, you know, willingness to approximate for the students. So that is part A. Okay, describing the scatter plot. This is a fairly common question. It seems like it comes up about once every other year or so. And if students are well trained, it should be really easy points. All right, so that is part A. Okay, part B. This was not asked on the actual AP exam. This is for us. Okay, it says calculate the equation of the least squares regression line and show it on the scatter plot. Okay, so I'm going to back out of the PowerPoint and walk you through this on my calculator so you can follow along. So we're going to press the stat button. Not a surprise that the stat button is probably going to be your most commonly pressed button in any stats class. Okay, we'll press other buttons, but stats going to be really common. We're going to move over to calc, okay, and we're going to go down and we're going to choose. I choose number 8. And so we had a conversation this week in my class. What's the difference between number 4, which says ln reg a plus bx, and number 8, ln reg a plus bx? Okay, I think I might have said the first one wrong. I'm replaying things in my head. Anyway, ax plus b or a plus bx. Okay, they're the same. I mean, it's, you know, commutative property. Doesn't matter what order you add those two terms in. It's just the way we're expressing this. So if a kid has used this in an Algebra 1 or a pre-calc class, they've almost certainly used number 4, because that's the way we tend to write equations of lines in algebra classes, is y equals mx plus b. But statisticians, they are sort of in their mind building towards multiple regression, where they can use multiple x variables. So they like to put the constant term first, and then, you know, in this case, b times x, or b1 x1, b2 x2 if they have multiple terms. Okay. I'll also point out that that's the way we write exponential functions, right? A times b to the x, right, where we have the constant first, or the y-intercept value, and then the adjustment. So anyway, that's what we use in AP Stats, but student would be perfectly fine using number 4. They wouldn't lose any credit or anything like that on the AP exam, but they should be able to recognize that the a plus bx really gives them the same thing. All right, so x list is L1, okay, y list is L2, find those in the same place. Frequency list, that's if you had a frequency table, which I suspect would be really unusual in a regression setting. So I just keep that blank. A store regression equation. You can do that in the, you can pull up Y1 and all that, and there's a series of buttons you can do, and I know there's some shortcuts. I typically leave it blank because we're going to have to write down the equation anyway, and then hit calculate. So calculate, there's our equation. I'm going to pull up the PowerPoint now because it's going to have that same screen there for us.
Hey, Josh, when you're switching over, I did get one question in the chat. When you mentioned the multiple regression, there was a question about if you had an extension of a single regression model that went to multiple regression. So just be thinking about that. Maybe something you could share at the end or something.
Okay. Yeah, so I'm not 100% sure I understand the question, but I'll let it percolate back there, and
there you go.
And hopefully we'll get something there at the end. All right, so there is our output. A is the y-intercept, and it reminds you at the top that you've got the y equals a plus bx. So A is the y-intercept, negative 545. That's obviously not a realistic value to interpret. You know, if a bullfrog was 0 grams, we'd expect it to, or 0 centimeters, we'd expect it to be negative 545 grams. That's yikes. That's an extrapolation, so we get some weird stuff when we do that. Then we get the 6.11 for the slope. Part B of that question actually asks students to interpret the slope, but we have a short amount of time here, so I'm not going to get too much into it. But you'd say something like, for each increase of 1 millimeter in length, the predicted mass increases by 6.116 grams. So the important part there is that we're describing the model, which means that we need to use the word predicted, because the model gives us the predicted value, not the actual values, as we'll see when we look at the scatter plot. Okay. R squared, we're going to discuss that a lot coming up, and R is the correlation. Okay. That's what it looks like on the screen. Okay, now let me show you how we can get that onto our calculators. I shouldn't have switched over so fast. So to get this equation on the calculator, there's a number of ways. okay, a number of ways. And different teachers have different preferences for showing their students how to do that. I'm old school, so I've written it down on my paper, and then I just type it into Y1. Okay, I know I'm not taking full advantage of the calculator's capabilities, and Curtis is probably cringing at this time. I don't know.
Only a little.
Only a little. All right. So negative 545.62 plus 6.1165x. And then I had turned this off so we wouldn't see it right away. So I'm turning it on now, and if I just hit graph again, it pops right up because I've already hit zoom 9. I've already hit zoom 9. So that's the scatter plot with the line. The line does a pretty good job. It hits some of the points really closely, but some of the points are fairly far away. So that's sort of the process we're going through here. The pattern in this the session is, here's our data, let's describe it. Okay, now let's find a model for it. Okay, and the model seems to work pretty well, but we want to ask another question, which is, how well does that line work? We've decided that a line is appropriate, but how well does that line work? And that's really the bulk of the rest of the talk. Okay, okay, so that's part C of this. Okay, how well does the line work? There's two ways we can answer this question. All right, two common ways. One is with R squared, the coefficient of determination. Okay, I don't really hear it called that much except in books, but most people just know it as R squared. But it's possible that the AP exam might throw that phrase out there, coefficient of determination, and it's important that your students know, oh, that's R squared. Okay, and this was part C of the actual bullfrog question, was to interpret R squared. Okay. And then with the other way we can answer this question is with S, the standard deviation of the residuals. Okay, we'll talk at the end, once we have both of those values, sort of the pros and cons of using each of those. They tell you similar information, but slightly differently. So each one has its value and has its place. All right, so before we go any further, we need to be clear on what we're comparing the line to, right? So when you say, how well does it work? Relative to what, right? That's the question that I think students don't get, okay? And I think it's my fault as a teacher that I haven't really emphasized that so much. But to understand R squared, you have to understand what you're comparing to, because R squared's measuring how well the line works relative to something. So what is that something, right? And that's the key question to make sense of this. So imagine we're going to select a 12th bullfrog. Okay, a 12th bullfrog. So we had 11 in the data set, right? So we're going to randomly select a 12th one. We haven't done it yet, but there's lots of bullfrogs out there. We're going to go get another one. What mass would we predict for this not yet selected bullfrog? Okay, so I'm going to give you a second. I don't see the chat, but I'm going to give you a second to think about that. Okay, think about what mass would you predict for another bullfrog that we haven't yet selected.
I just saw in the chat, we have Chris responded 83.3% of the response variable mass of the bullfrog can be explained by the model least squares regression line.
Yeah, so that's getting to the interpretation of R squared. Okay, so it's that phrase of the variability that is what we're trying to focus in on and try and understand of the variability and what, right? So what happens when I talk about this with my students will say, oh, well, how long is the bullfrog, right? Because they have this line and they know that the association's positive, and if they knew the length, they would be able to predict the mass pretty well. And I said, that would be great, but we haven't selected the bullfrog yet, right? So we don't know how long this bullfrog is. So eventually we get around to saying, oh, the mean mass, okay? Right? If we didn't know anything about this 12th bullfrog and we're trying to predict the mass, well, we have 11 bullfrogs and we have 11 bullfrog masses. So we could just use one variable stats on list 2, right? And we would get the mean mass, which is y bar 370.18, okay, 370.18. So I jumped ahead of myself. So let me go show you where this is on the calculator. So if I want to calculate, means and standard deviations and all that. I'm going to press stat. Okay. I'm going to go to calc, and I'm going to choose one variable stats. And in this case, I don't want mean length. I want mean mass. Masses are in list 2. So I'm going to go second 2 to get to list 2. Frequency list, again, I don't have a frequency table here, so I'm going to leave that blank and calculate. And you can see the mean is 370.18. 370.18.
Yeah, we had a couple of people mention 370 grams.
Good. All right. Okay. So we could look at what that looks like, right? Because that's really essentially a different model. Okay. So I'm going to put that as 370.18. I'm going to temporarily turn off this line, which is, hey, that's a great feature if you don't know about it. If you want to have an equation not show up, you don't have to clear the whole equation. You can just press enter on the equal sign and it'll turn it off, but you'll still have the equation there, so you don't have to retype it in later. Okay, so maybe everybody already knows that, but when I discovered that, I thought, oh, that's a helpful tool. All right, so there's my graph with the data set and just guessing the mean mass. Okay, well, it does pretty well for one of those points, but not for a lot of them, right? So that's what we're comparing to. We're saying, well, if we don't know anything about length, we'd have to use mean mass as our prediction. How well does that work? Okay, not that well, as it turns out. Okay, and so we can measure in terms of like how well it works, thinking about sort of an average distance from the model, right? How far on average those dots are above and below the line. Okay, so we could do that. I'm going to go back to my stat editor. Darren, don't worry, I see the time. I'm not going to go. I'm going to try and work through this pretty quickly. So what we have in list 3, I want you to go to the heading of list 3, not the first entry spot. Man, this happens every time with kids. You tell them, go to the heading, go to the heading, go to the heading, and they still don't do it. Like, make sure L3 is highlighted. And what we're going to do is we're going to do L2, which is our actual masses, minus 370.18. Okay, so in the heading of L3, I did see that, chat.
You did see that, chat? That's awesome.
0.18. So these are the distances each point is from that naive model, that simple model of y equals 370.18. Okay, so if we want to find the average residual, okay, that's what this is. These are residuals. If we want to find the average residual, we can go stat, calc. Okay, we'll do one variable stats on list 3. List 3. Calculate those, and we get an X bar of 0.0018181818. Really, that's 0. I just didn't type in all the decimal places for the mean, but if I had done the exact mean, that would be 0. Again, because the positives and the negatives cancel each other out. Okay, we've seen this problem back in one variable stats, right, when we were doing standard deviation. Okay, and our solution there is going to be our solution here, which is we don't use the average value, we use the sum of the squared values. So you can see the third line is sigma of x squared. So that takes each residual and squares them to make them all positive. And then that is our sum of squared residuals. So that's sort of our baseline. If we don't know anything about length and we just use the average mass, how well does the line work? Well, the sum of the squared deviations from the line is 103,153. 103,153. And so when we talk about percentage of variability that's explained by or accounted for, that's this number, the variability of mass from its mean. Okay. Now, I'm going to go back to the PowerPoint, and I'm going to not go switching back and forth between the calculator now. I'm going to zoom through this to sort of wrap this up. Okay, so that's what we looked at. Okay, we talked about how well the line worked. We're going to find the residuals. We did that in list 3. Okay, what is the average deviation? We saw it was basically 0. So we solved that by squaring, and we got that 103,153 number, or 154 if you round. So plop that in the back of your mind. Okay. So now when we're thinking about how well does the line work, now let's think about the least squares line. All right, so that's what we started with. Here's our least squares line. Does it work better? Sure works better, right? Because the line, the diagonal line, is closer on average to those dots. Again, the average residual is going to be 0. So what we want to do is figure out the sum of the squared deviations. So in list 4, we're going to put the residuals from the least squares regression line using the residual list. So you can see in the screen capture there, in the highlighting L4, it's calling out the residual list, which is in your list menu, which is second stat. Second stat gets you the residual list. You can find it there. But that only works after you've calculated the regression line. It has whatever residuals are in there from whatever regression line was calculated most recently. So you can pop them into list 4. You can find the average deviation. Again, it's 0. It says negative 1.63 times 10 to the negative 11th. So we're going to look at the sum of the squared residuals, which is now 17,250. Remember, it was 103,000 earlier. So 17,250 now. Okay. And so that's our sort of wrap it up thing. How much did the sum of squares residuals go down when we used the least squares line instead of the mean only model? Right, so I did a little subtraction. We went from 103, 154 down to 17,250. That's a decrease of 83.3%. It's just a percent reduction, okay? That's all we're doing. You just have to know what we're reducing from. And that's where I think students really struggle. So that's our 83.3%, okay? That's R squared. So you can say when using the mean, when using the least squares line, the sum of the squared residuals goes down 83.3%. Compared to using the model that uses the mean mass only. That's really long. So statisticians have shortened it to say 83.3% of the variability in the mass of the bullfrogs is accounted for by the linear model using x equals length. Okay. Of course, R squared showed up on the output when we calculated the line originally, and that's that 83.3%. So the variability is the variability in mass measured as sum of squares from its mean. Okay. So really quickly, we can also use those sum of squared residuals, each of them, to do another calculation that's interesting. Okay. Remember back in unit 1 of AP Stats, we calculate just regular standard deviation, deviations from the mean, divide by, square them, divide by 1, n minus 1, take the square root. So if we did that with our 103, 154, just thinking about mass, that's 101.6. So the bullfrog masses typically deviate by about 100 grams from the mean mass. But if we use the least squares regression line, we use the sum of the squared residuals from the line, divide by n minus 2, because we had to estimate a slope and an intercept in our calculation, and we get 43.8. So that's a way of thinking about sort of a typical residual. So the typical residual has been cut by, it's more than 50% smaller when we were able to use the least squares line. So that's another way to think about how well the line works. You can think about it as a percent of variability that's accounted for, or you can think about a reduction in the standard deviation of the residuals. Standard deviation is nice because it's in the units of the question, it's in grams. R squared is nice because it's on a standard 0 to 100% scale. You don't have to know anything about the context to make sense of R squared. All right, so that's that. And my part is done. So I will kind of be looking in the chat, and if you have questions, we'll try to address those at the end. So Darren's turn.
Thanks, Josh. Just want to confirm that you're seeing that same slide on my screen.
You're not in full screen mode, but yes, we're seeing it there.
Yeah, didn't want to be in full screen mode. So I'm going to jump ahead a little bit to Unit 4 and a little bit of Unit 5, talking about random variables. So the title of this particular problem is Doing the Floss, Grin and Bear It with Random Variables. And I knew when I picked the title that some of you would have a different image in mind than what I did. So if this is what you're thinking.
Yes!
Mom.
What are you doing?
Doing the floss.
Yeah, that's not what I'm going to be doing. So But now you've seen the floss anyway. This is a fun problem that came out of, well, dental floss. Some of us have been encouraged by our dentists to use floss more regularly to keep our teeth healthy. And I had been noticing that when I went in the morning to pull off my piece of floss, there was a certain amount of floss that seemed to be the right amount. And I wasn't always getting the same amount of floss, even though I was trying to. And Curtis, by the way, the price of admission would be better if I would do the floss, but maybe in a future
We would have
session
had to charge significantly if that was the case.
Josh took an extra minute, so I wasn't able to fit that in this time, but maybe next time. So here's the story.
All waiting for that floss. Yes.
Yeah. So here's the story. Flossie McFlossington is our character today, and Flossie flosses her teeth once per day. The amount of floss that Flossie pulls off the spool on a given day, you can picture this little floss, can be modeled by a normal distribution with a mean of 17.1 inches and a standard deviation of 0.9 of an inch. So we've got a few parts to the question. This first one is going to be kind of a hopefully straightforward probability question, but we'll see. So from experience, Flossie needs at least 16 inches of floss to clean between all of her teeth. What is the probability that Flossie pulls off too little floss on a given day? Now I slowed down there and sort of read it because I know that students don't always do that. And so maybe they were thinking they're supposed to find the probability of at least 16 inches of floss, but that is not what we're trying to find here. We want to find the probability that Flossie pulls off too little floss. So one of the things I want to do is similar to what Josh did, talk a little bit about how the AP exam has been emphasizing these random variable probability questions in the past few years since the course and exam description came out. One of the skills that students need to be able to demonstrate is the ability to define a random variable. They may be asked to do it as a part of a question, or they maybe should be put in the habit of doing it by their teacher so that if they're asked to do it, it becomes a habit. So in this case, I've defined the random variable as X equals the amount of floss that Flossie pulls off on a given day. The next skill that they want to have is the ability to talk about how a particular random variable is distributed. What is its probability distribution? So in this case, we want to think about the stem of the problem. We're told that the amount of floss Flossie pulls off can be modeled by a normal distribution. So this random variable is normally distributed with a mean of 17.1 inches and a standard deviation of 0.9 of an inch. So when students are asked how a random variable is distributed, they're not just supposed to say normal. They need to talk about the distribution and any parameters associated with that distribution, in this case, the mean mu and the standard deviation sigma. And then the other key piece is for students to be able to identify what values are of interest in a particular problem. So that's why I was emphasizing that question here, too little floss. We want to find the probability that X is less than 16. That would be not enough floss for Flossie to floss all her teeth that day. So none of this is calculator related. This is all about how to solve a probability question involving random variables. And I'm going to model this approach on the other two parts of the question just to kind of get it to be a habit. So my advice is to have your students do these moves on each random variable probability question when you get to that part of the course so that it's second nature to them. They won't forget it. All right. So the next thing I want to do is jump over to the calculator. I'm going to pull mine up here and show a few things that might be of interest to you when you're teaching this unit. If we go into our y equals menu, we had our regression line there from before. I was playing along. And so I'm going to go on to the equal sign and press enter to turn it off. I also see plot 1 is turned on right now. So I'm going to go up to plot 1 with my arrow keys and press enter to turn that off because I don't want any of that to show up right now. And in my y equals menu, it looks like y2 is available. So I'm going to put in a normal probability density curve, which is in the distributions menu. We're going to be spending most of my part of the talk in the distributions menu. So if you go to second vars, normal PDF, which doesn't get used very much, is the perfect thing to draw the normal density curve. For the X value, we just want X. And for the mean and standard deviation, we want to match what's given in the problem. So 17.1 and 0.9. And if I come down here, so I have a newer operating system than some of the students do. If they're just typing in the command, they don't have the little wizard menu. So they just do normal PDF parenthesis X comma 17.1 comma 0.9. Now, if I just try to graph that, the window setting is based on the regression model that Josh fitted a minute ago. So that's not going to be the right window. We need to do some window management. So if you press window, we can go in and set up a reasonable X scale, and I can help you out with the Y scale a little bit because I cheated, tried it out earlier. So if for the X minimum, we do like 17.1 minus 3 standard deviations, because we know that most values in a normal distribution are within 3 standard deviations on either side of the mean. So 17.1 minus 3 standard deviations and 17.1 plus 3 times 0.9. Then we have a pretty good interval for our x-axis, and I'm going to use the scale of 0.9 because that's the standard deviation, and I'd like the tick marks to show that. For the y-min, I'm going to go 0, and for the y-max, I'm going to go 0.5. Again, tested that a little earlier, and when we're ready, we'll just hit graph, and we'll get a pretty normal curve. Unfortunately, it doesn't identify the values of interest because we're just graphing the density curve. So if you encourage your students to draw a normal curve and shade in the area of interest, which I have my students do, we need to do one more thing to get the area of interest shaded. And that's under the distribution menu, draw. If we go to shade norm, I want to shade everything to the left of 16. So 0 would be the lowest because we can't have less than 0 floss, and the upper would be 16, and the mean was 17.1, and the standard deviation was 0.9. I also like blue. Having gone to the University of Michigan might help explain that. So we'll keep it blue for the shading. And the advantage to doing that is we now see the answer to the problem down there in the display. So we can do a little checking when we get to the calculation part here in just a second. All right, so for those of you that haven't used normal PDF very much or ever, or haven't used shade norm, there's a little illustration of how you might be able to use those to help your students visualize what they're doing. Also maybe to help them sketch their curves a little better so it looks more like what you see on the screen. So let's talk about calculating the probability. Well, I'm sure there are a bunch of math teachers like us on the call who, when you think calculate the probability, you're thinking, got to do a formula. So let's get that out of the way first. For those of us who like using a z-score formula, we can take the boundary value of 16, subtract the mean, divide that difference by the standard deviation, and get a z-score of negative 1.222. And then to find the area, we need to use the calculator to find the area to the left of negative 1.222. So let's come over here and do second variables or distributions. We want the area underneath a normal curve, so that's normal CDF. And we want, ooh, I actually turned off my wizard there. There we go. Didn't mean to hit enter that quickly. So I want to go from 0 to 16 with a mean of 17.1 and a standard deviation of 0.9. Again, for students that don't have the wizard, they're just typing in the command like this on the home screen. That's a definite disadvantage for them if they're using an older machine, that they have to sort of get the syntax correct like this. Except I didn't get the syntax right. What did I do? Did I do? Ah, did normal CDF twice. Let's try it just once. Oh, that number looks familiar. That's the same number that I had underneath the graph on the previous slide. Now, if a student were to write down what's on that calculator screen as their only work on this problem, that would not count as appropriate work. Why not? Because the inputs of the command are not clearly labeled. So a naked calculator command on its own is not sufficient for work. A z-score formula, that's good enough for work. A labeled calculator formula would be good enough for work. So you saw how I got the 0.1109 from the calculator. My work here is the z-score. And there are the screens to just sort of remind you what I did. Some of you who are more contemporary, if you will, and aren't into the sort of formula approach might think, why don't we just use the technology? I mean, this is a technology talk. Well, I would say, well, back in the old days, we used to use a table. So that was my technology when I learned the course back in the 1900s. So you could use a table, but then you'd have to round your z-score to only 2 decimal places and like look it up from the rows and columns of the table. Let's dispatch with that old technology.
That was on papyrus, right?
Yeah, back in the old days, there was some kind of scroll and all that.
Yeah, had to unroll it.
You might want to just go straight to the normal CDF like this and write that down. The problem is you have to write down the inputs that you see here. So if students are going to use the normal CDF on the calculator, they do have to write down the lower bound, upper bound, mean, and standard deviation. Those labels could be labeled with words, could be slightly abbreviated as it is on the screen, lower, upper, mu, sigma. Any of those abbreviations would be fine if that's the work that's being shown. So again, 2 options for showing work. One is sort of the z-score and then use technology or a table to get the area. The other option is just use technology to begin with. I actually make my students show the z-score calculation each time. I'm still a little bit old school. I don't make them use the table. However, they're welcome to use the technology to get the area. So I've spent a little bit longer on part A just to sort of talk through the AP exam scoring tips, like labeling all the inputs of the calculator command. Hopefully I've not beaten that horse for too long, but let's get back to the other 2 parts of the question. So old Flossie flosses her teeth every day, once a day, and this particular month that we're in has 31 days. So we want to find the probability that Flossie pulls off 2 little floss on more than 2 days in the month. So 2 little floss again is less than 16 inches, more than 2 days in the month. All right, so I need to regroup here. This is a new situation, and we're going to follow the same routine. Define the random variable. I'm not going to call it x because that's already used. So let's let y be the random variable here. We'll make that the number of days in the current month when Flossie pulls off 2 little floss. And that's the event we found the probability of in part A. State how this random variable is distributed. Well, students might be tempted to say normal, and that would be bad because y's values can be anything from like 0 days, 1 day, 2 days, all the way up to all 31 days. We could pull off 2 little floss theoretically. So it's a discrete random variable taking on values from 0 up to 31. So this one's a binomial random variable. The number of trials is 31 of this random process of pulling off a piece of floss, and the probability of success, i.e. pulling off 2 little floss on a given day, is 0.1108. So 2 little floss is what we're interested in here. And then we want to find the values of interest of the variable. So we want the probability of y being, well, more than 2 days. So the probability that y is greater than 2. So again, that's just the setup. I'm trying to encourage you to think about having your students develop as a habit, practicing defining the variable, stating how it's distributed, and then identifying the values of interest. Now let's get to the calculation part. I made a pretty picture here to try to model what I did with the normal distribution. And if you're curious how I made the little picture, This is kind of fun with a discrete random variable, either binomial or geometric. If you go into your stat editor, and we have an available column here, I think Josh used up through L4. So if I go into L5, I can put in the values from 0 to 31 with a sequence command. So second stat is my list. If I go to ops or operations and come down to sequence, I can give the expression as x and the variable name is x, start at 0, go to 31 by 1. Again, if you're on an older operating system, you just get the command showing without the wizard. But it basically is going to generate a sequence of numbers, the rule being x starting 0, 31 by 1, making sure I'm highlighting L5, and that just puts in the numbers from 0 to 31. In L6, I want to do their probabilities. So I'm going to do second distribution while highlighting L6, come down to binomial PDF. Trials is 31, probability success 0.1108, and the X value I actually want to use the values in list 5 or L5. So that was second 5. If I paste that in, it will give me the probabilities that correspond to each of those values of Y. And then the last piece to make the graph is in my stat plot. If I turn on plot number 1 and make it a histogram, my X list is not L1, it's L5. And my Y list would be the relative frequency in this case, which is L6. Again, the window management, you're going to have to adjust the window manually. You can't do zoom stat and get a good graph here when you use a frequency list, or relative frequency list in this case. So I'm going to go from like 0 to 31 by 1 in my window. And then for my Ymin and Ymax, let's try something like 0.3 as the maximum this time. And of course, I forgot to turn off my normal curve from the last problem. So I don't know if you ever do that, but my students are used to me doing that in class, leaving something turned on from before, so I just turned that off. So here's the binomial probability distribution, and if you hit trace, you can see the individual probabilities for each value. I just like to have a way for the students to visualize it, not just think of doing a calculation, but kind of analogous to the normal curve area. We're trying to find the probability of Y greater than 2, so that's going to be everything from 3 all the way to the right. That's a pretty large probability, I think. So let's find it. You know the routine. We can calculate the probability with a formula. Math teachers among us realize that the formula we have is the binomial probability formula. It's actually given on the AP exam formula sheet. So the problem is we don't want to do too many applications of that formula. So we don't want to find like 3, 4, 5, 6, 7, 8, all the way up to 31. That would be a lot of applications of the formula. So if we use the complement rule, we only have to do 3 applications of the formula, and we can subtract from 1. So I went to the trouble of like copying that out and putting it into some sort of equation editor for us. So you could definitely do that, and that's a full credit approach. For those of us who like that sort of stuff, it looks really beautiful. There is another alternative. We can just use technology. So in the calculator menu, we'd go to second vars and look for binomial cumulative. I did it again. Hit enter too quickly. Second vars, binom. Just hit enter once. There were 31 trials with a 0.1108 probability of success on each trial. We want the probability that Y is greater than 2. Well, the calculator does probability that Y is less than or equal to a certain value. So if I do this, that's not the right answer. But if I take and subtract 1 minus that answer, that is the correct answer, 0.6829, the one we got with that beautiful formula. Again, if students are going to use this as their work, and they're not going to show the binomial probability formula, they must label what the inputs of the command represent. If they do not label the inputs of the command, it's a naked calculator command. It does not count as work. Are we having fun with floss yet?
We're having a ball.
Yeah. All right, well, here's one more to cut your teeth on, so to speak.
Oh,
Yeah,
that was bad.
thank
That
you.
was really bad.
Yeah, keep that one for your evaluation. Part C is the obvious question at the end, like, okay, so the month had 31 days and the spool started out with 45 feet of floss. What's the probability that Flossie will run out of floss by the end of the month and have to like go get a new thing of floss? Well, we've got our third and final random variable here. I've used X and Y, and some of you might be thinking, oh, I bet he's going to use Z. No, he's not. He only uses Z for a standard normal or a standardized situation. I don't use Z and I don't use T when I'm doing random variables unless I mean something with Z or T as in standardized. So I'm going to define a random variable that to me makes better sense, which is T as the total amount of floss that Flossie will pull off on these 31 days. And it's the sum of the floss that she pulls off on day 1, floss she pulls off on day 2, all the way up to day 31. It's the sum of 31 identical random variables. How's this one distributed? Well, thank goodness all of us know that there's a theorem about what happens when you add or subtract independent normal random variables. If you didn't know it, you're about to. Basically, the theorem says if you have independent and identically distributed normal random variables, the sum or difference is also normally distributed. The random variables have to be independent. That's the one catch for the theorem. So we're going to have a normal distribution to model T, and its mean is going to be the sum of the means of the 31 individual random variables. In other words, it's the expected total amount of floss that Flossie would pull off in the 31 days. And not surprisingly, it adds up to 31 of those 17.1s or 530.1 inches. Now, for those of you who haven't taught the course much or ever before, the standard deviation is not quite so nice. Wouldn't it be great if we could just add the standard deviation together 31 times? Wouldn't that be awesome? Yeah, that doesn't work. There's no theorem like that. Standard deviations don't add. But when you're adding together independent random variables, variances do add. So the variance of the total is equal to the sum of the variances for these 31 individual random variables that are identically distributed. So that would be 0.9 squared added together 31 times. If I had more room, I would have preferred to write it out as 0.9 squared plus 0.9 squared plus 0.9 squared 31 times. And I know Josh prefers that written out also, but I ran out of room here on the slide. So I wrote it as 31 times 0.9 squared. I got 25.11 for that, and I took the square root to get back to the standard deviation because I need to do a normal calculation based on the mean and standard deviation. So in identifying the values of interest, well, we want to find the probability that she'll run out of floss. So that would be that she uses 45 feet or more before she gets to the end of the month there. Okay. So 540 is the corresponding number of inches. I did 45 times 12. And then once again, we can use our z-score method. The probability that she uses up 540 or more, we get a z-score of 1.976. I used my calculator to do that as a normal CDF, but I'm not using normal CDF as my work. Or there's proof that I did it. You could use table A and round your z-score. We talked about that. Or you could just go straight to the normal CDF command on the calculator, which I did there. Students would have to label that set of inputs in order to get credit for the work. And there's obviously more work on this part in terms of finding the mean and the standard deviation that they'd have to show in order to get full credit. So I think we've flossed enough. Reminding you that the slides with all the worked out details, in case you need to like rewind any part of this, will be available. And so I'll stop sharing there if that's all right, Curtis.
I think that's perfect.
Yeah.
Absolutely perfect. Well done, everyone. Both of you guys did a fantastic job. Thanks a whole lot. I know that, Darren, real quick, I do need the last slide. I think there's
Yep,
a slide in there.
there was, yes.
In there. So I want to make sure, or was that the last slide? I can't remember.
No, you had another one. There it
I
is.
do have one more. So we do actually have a random drawing during the session today, and we have a graphing calculator. So one person who wins that graphing calculator is Shanna Farrell. So Shanna, your name has been randomly selected from the list here. So Shanna will be contacting you to make sure that we get all of the things for you. I know Josh actually had a quick response to the multiple regression piece here, so he dropped a link in there. So Josh, you've actually got a minute if you want to respond to that directly.
Yeah, sure. So in the summer institutes that I do with experienced teachers, we do dip our toes a little bit into multiple regression. And so what I did 2 summers ago was expanded that bullfrogs data set. And I just made up some other variables, girth, like distance around, like, the waist size might help explain why some frogs are heavier than expected based on their length and others are lighter. And then some other variables that either help or don't help. And we have fun exploring those sorts of relationships. So I posted a link to that data set that I made up. Granted, I made it up, but I made it up for educational purposes to try and illustrate some of the key ideas of multiple regression. So hopefully that is helpful.
That was perfect. That's a great resource. Thanks, Josh, for sharing that. Thanks, Josh and Darren, for all your prep work and for sharing this this information with all of us. I hope everyone enjoys the remainder of the conference. I know we've got a few more sessions throughout the rest of the day, so I'll stop this one and you guys can go join your next one.
Thanks, everybody,
Bye.
for coming.
Thank you. Thanks, Curtis.
Thank you.
Curtis.